Okay. Assalamu alaikum. Acha, so we will continue now today again with the time evolution of the wave function. टाइम एवोल्यूशन ऑफ अ वेव फंक्शन क्यों इम्पोर्टेंट होता है वो सारी चीज़ें भी डिस्कस हो जाएंगी और we will develop a very important time evolution of a wave function formalism which is known as the path integral formulation due to Richard Feynman. And you would see in this path integral formalism that it is very much consistent with our classical intuition, what basically, in fact, time evolution of a wave function means classically, or in a classical intuitive sense, कि हम उसको किस तरह से कोरिलेट कर सकते हैं वट एवर वी हैव our understanding of a quantum system with the help of the wave function. So it is, you see, it is very important about understanding quantum system in classical sense. Why? Because when we talk about the time evolution of a quantum system, it is n obviously defining that time evolution of a quantum system in position space. So the intuitive sense from quantum mechanics does not come into our minds readily, and that intuitive sense can only be obtained through classical description. Yeah, and that is basically what Richard Feynman did while developing the path integral formalism. So हम path integral formalism शुरू करेंगे. So we will continue with our understanding of the time evolution of the wave function, and obviously we will continue with the our understanding of the time evolution operator, which is the unitary operator. उसी की मदद से हम ये चीज develop करेंगे. So we will uh, continue with the time evolution, with the time evolution of a quantum mechanical wave function uh, using our our classical intuitive sense of time evolution. Time evolution of quantum mechanical system. Yeah, so that is our main idea, कि हम किस तरह से टाइम एवोल्यूशन को समझ सकते हैं, क्वांटम मैकेनिकल टाइम एवोल्यूशन को समझ सकते हैं. एंड दिस विल then give us a profound formulation in quantum mechanics, which is, as I said earlier, which is known as the path integral formulation for understanding quantum mechanics. So this will sort of uh, will then give a profound understanding formulation in quantum mechanics. And what is that? Uh, what what is that means? What is that formulation? That is namely path integral formulation for understanding quantum systems, or for understanding the time evolution of quantum systems. Yeah, so this is This is important. And so when we talk about time evolution, so the first thing which comes into our mind is the time evolution or time dependent Schrödinger equation. So as usual, we will start with time dependent Schrödinger equation to understand this new type of formalism. And remember, ये बहुत important formulation है. Even if you don't go into sort of research in particle physics or theoretical physics, even then it is very important. And all those people who are interested in doing condensed matter physics, this formalism is important for them as well. To understand how the system evolves as time goes on. So remember, quantum systems, they are described in some position space, and these quantum systems, they are continuously interacting with their environment, and because of that interaction, they evolve in time. Yeah. And so one needs to know what is the effect of that interaction in time. And so that is important. That is, the time evolution is important. Yeah. So let's start with the time evolution equation, which is the time dependent Schrödinger equation. So let's start with time dependent Schrödinger equation. And what is that time dependent Schrödinger equation? Up to now, आपको रट गई होगी. That is psi psi dot, which is in fact d psi by dt. Yeah. And then we have in fact the spatial part, which is minus h bar square upon 2m times del square psi plus the potential V psi term. Yeah. So this is the time dependent full time dependent Schrödinger equation, at least in gross terms, where we have the kinetic energy term and the potential energy term. Yeah. And so we have to think about that this is time dependent Schrödinger equation for a bound system, because we have specified this factor, which is basically the potential. Yeah. And so and that is also important why we are using the in fact time dependent Schrödinger equation for a bound system. We could have started with the free particle as well, but then the potential is basically something which is a classical concept. And what we have started saying about in fact a path integral formulation, that Richard Feynman basically invented or formulated this new formalism such that he correlated, in fact, the two disciplines, that is the quantum mechanics and the classical mechanics, and such a correlation, which is a very good correlation, in fact, is achieved through path integral formulations. And so we need to have not only the wave function psi, which is a quantum sort of object, but we also need to think about other terms in the time-dependent Schrödinger equation as describing some sort of classic quantum mechanical system in terms of classical mechanics. Yeah. Okay. So the physical interpretation of psi, you can think about the physical interpretation as psi being the probability density, which is nothing but norm squared of psi. And norm squared of psi का मतलब होता है rho. If the probability density is rho, then this probability density rho is equals to psi star psi, which is the norm squared of psi. Yeah. And so we start with the physical interpretation of the wave function. Uh, so the physical interpretation of psi can be obtained by thinking about probability density. yeah, which is rho, probability density rho, uh, which is in fact norm squared, norm norm squared ऑफ साई, आई क्या होता है, रो बराबर होता है साई स्टार साई, yeah, so which is in fact the probability of finding the particle, and obviously it is when you talk about the probabilities at density, so you do not just talk about probability of finding the particle somewhere in some three-dimensional space, or somewhere in a four-dimensional space or so on, but you also have to say that this has to obey some sort of a equation which describes the flow of the probability, which is known as the continuity equation. Yeah. And so what is this? Which is the probability of finding probability of finding uh, finding the particle, uh, and which obeys uh, the continuity equation. And what is continuity equation? Continuity equation is rho dot, that is the rate of change of probability density, and the probability density, which is the probability of finding a particle, can only change with respect to time if there is a flow of probability, and that is basically described, that flow of probability is described the divergence of सम क्वांटिटी, सम वेक्टर क्वांटिटी, जिसको प्रोबेबिलिटी करंट कहते हैं. सो रो डॉट वुड बी इक्वल्स टू माइनस डेल डॉट जे. डेल डॉट का मतलब है, डेल इज द कर्ल ऑपरेटर, एंड दिस इज in fact, sorry, del is the three dimensional operator, not the curl operator. This three dimensional operator del describes the divergence of some vector quantity, and in this case the divergence of vector quantity is in fact, that vector quantity is the probability current density. So you can think about the first term in this continuity equation as the rate of change of probability density, and then you can ask in your mind how the probability density would change. So the probability density would only change if there is a flow of probability density. And what do you mean by flow of probability density? The flow of probability density is known as the probability current. Yeah. And so this probability, if there is the divergence of probability current density, then that would be equals to minus of a rho dot. Yeah. And that is your continuity equation, which is basically not, in fact, just the feature of quantum mechanics. It is also a feature of the fluid dynamics. It is also the feature of electrodynamics. In all those disciplines, wherever we would like to see some sort of a flow of fields, then we talk about the continuity equation. So those fields, those probability densities, those fluid fields, they are always defined not just by their own description, as here we talk about the probability rho as probability density of finding the particle, but they must also obey some sort of an equation which is known as the continuity equation. So the complete definition or description comes out about comes out in two steps. Number one, the probability density, which is the probability of finding the particle. Number two, it has to obey some sort of continuity equation, yeah, which is basically this equation where where this your J, where J is the probability current density, and this is equals to iota h bar upon 2m times some factor where we have psi star del psi plus del psi whole star psi. Yeah, so this is some equation which is in fact your current density equation. Yeah, and we can always take the imaginary part. Uh, we can start with the imaginary part, and so the imaginary part, or rather the कॉमन फैक्टर को हम बाहर कर लें, यानी आयोटा एच बार वाला फैक्टर जो है वो बाहर हो जाएगा, और सिंस वी आर टॉकिंग अबाउट द इमेजिनरी पार्ट ओनली, so that would be h bar upon 2m, and the imaginary part of uh, psi star del psi. So we are taking just the imaginary part. So this continuity equation is in fact a simple consequence, or basically you could say the result of taking the expression from probability density, and you plug it into the time dependent Schrodinger equation, and then using it to drive the expression for continuity equation, or using or to drive the expression for rho dot, which is the time derivative of the probability density. And then you could say that this rho dot is equals to what? It is equals to the gradient of something, and that something is known as, the probability current density. And then you can compare it to our understanding of fluid mechanics, and if you if you are able to compare these concepts from fluid mechanics, then basically you would arrive at some mathematical formalism of path integrals. Yeah. And so this is important. So let me write this. So what you need to do. Uh, so so this is uh, continuity equation, which is a simple consequence, or or result of taking the expression for probability density. Yani you start with rho is equals to psi star psi, yeah, and you then and plugging in plugging it into the time dependent Schrodinger equation. Yani you start with the rho is equals to psi star psi, and then you start using the Schrodinger equation, take the complex conjugate, which is psi star, and then you substitute that psi star value, and you substitute that psi as a time dependent Schrodinger equation, and then you solve it, and then whatever comes out is the derivation of the expression for rho dot. Yeah. And time dependent Schrodinger equation, and then using it to drive the expression for rho dot, which is which is equal to the equal equal to the gradient of something. That something is in fact j, del dot j, and then you compare it, and comparing it our classical understanding, comparing it to our understanding of fluid dynamics. Of fluid dynamics. Yeah, so this is basically something जो हमें lower classes से पता है. Yeah. And so रो क्या चीज़ है? बार बार मैं इसको emphasize इसलिए कर रहा हूँ कि what is rho? Rho is the probability density. So इस probability density को we can also call it as the likelihood of finding a particle at some position as a function of time. Then when we say likelihood, so it is somewhat a classical description of rho. So what is rho? Rho is probability density, i.e. likelihood of finding a particle at a given time, at a given position as a function of time, is a function of time. And obviously, remember, इस चीज को कैसे लिखते हैं? X is equals to x of t, which is purely a classical description of position. That is, you specify the position of a particle at a certain time, which is deterministic in classical mechanics. But when we talk about quantum mechanics, the position, determining the position of a particle is not deterministic but probabilistic. So we use the words probability density or likelihood of finding the particle at a given position at which is a function of time. Yeah. दूसरी चीज जो है important वो J, and what is J? J is the probability current density, because it needs to satisfy the continuity equation, current density, or current, basically probability current. Yeah. So what it means is that although quantum mechanics, it is hard to understand, but it has some sort of similarity with classical understanding of our world. So maybe I have made my point by giving you an idea that yes, we can basically describe the quantum world or quantum systems using our classical sense of understanding this universe. So, so it is basically some sort of a premise, or it is basically some sort of an argument which was given by Richard Feynman, that we can describe quantum system with a new formalism known as the path integral formulation. So this is sort of an argument, or 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 or, or some sort of a claim by Richard Feynman that yes, it can be done. Yeah. So 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 one can think. So it means that quantum mechanics, though hard to understand, nevertheless, it has similarity, similarities, or rather similarities with our our classical understanding of the world. Yeah, so we can somehow we can do this. So for example, probability of finding a particle at a given point in time obeys some local conservation law. So we are very much used to of conservation laws in classical mechanics. So the probability of finding a particle at a given point is point in time that has to obey local conservation law. And why it has to obey local conservation law? Because then from continuity equation, just as for any continuous mechanical system, we can also do the same. So the change in probability of observing the particle at a given point in time is proportional to the flux of probability out of that point as a function of time, which is nothing but the physical interpretation of a continuity equation. Yeah, and this is a uh, very important, in fact, you could say, claim that quantum mechanics can be described classically. Uh, so, ex- so for example, uh, probability of finding a particle at a given point in space, point in space in some time, obeys local conservation laws. क्या मतलब? i.e. continuity equation, continuity equation, just as for any continuous uh, mechanics, for any continuous mechanical system, So it is also true the for the quantum system. So the change in probability of observing the particle at a point in time is proportional uh, to the flux. And what is flux? Probability current. Flux of probability out of that point, out of that point as a function of time, as a function of time. And what is this? This is the physical interpretation of continuity equation. Yeah, right. Physical uh, interpretation of continuity equation in quantum mechanics, which is very much consistent with our classical notion or our classical concept of continuity equation as we have learned in the fluid dynamics or electromagnetism, or in mechanics, or any classical description of our universe. This has the same sort of description. Only the difference you would feel would be saying some very important and technical terms we have used here, And one of those technical term is this observing. And when you say observing, so we hear an observer such as position observer, the momentum observer, and these observers, they are basically observed using some operators which are quantum mechanical operators. So the mechanism of sort of observing the particle may be different from classical mechanics, but the idea, the basic idea is the same. So since the basic idea is same, so we can develop some sort of a correspondence. That is, we can develop some sort of a formalism which is consistent with our classical understanding of nature. Yeah, and so that is what the idea behind path integral formulation. Uh, but we need to identify those very specific sort of unique properties which are unique to quantum mechanics and not obviously seen in classical mechanics, and those unique quantities there that would make a difference between though the formalism is same, though the approach is same, but the mechanism of sort of understanding those two disciplines are different, and so it is different from classical mechanics, and that is what we need to develop in path integral formulation. And this can help in understanding the concept of quantum mechanical wave function. So not only we will, so आप लोअर क्लासेस में जब होते हैं तो यूजुअली जब आपके पास ये मैथमेटिकल ऑब्जेक्ट आता है जिसको आप वेव फंक्शन कहते हैं psi. So usually it is something which is not very well understood, and at times we are struggling to describe the wave function. And so if somebody asks us what is wave function, what we can only give the mathematical description of the wave function. But we are not able to describe in an intuitive manner or in some classical manner as we basically define or describe things in classical mechanics. We are unable to describe wave function as classically as we do in classical mechanics. So इस फॉर्मलिज्म में आपको ये भी फायदा हो जाएगा कि आप वेव फंक्शन को बहुत बेहतर तौर से डिस्क्राइब करना शुरू कर देंगे. सो दैट इज आल्सो द एडवांटेज ऑफ फाइनमैन के पाथ इंटीग्रल फॉर्मलिज्म का कि वेव फंक्शन भी डिस्क्राइब होना शुरू हो जाता है. सो this can help in understanding the concept of quantum mechanical wave function. So this is also important. Now, what is a wave function? Wave function is some complex quantity, yeah? And the norm of the wave function is something which is a real quantity, which is the probability density. But in addition to these two definitions or descriptions about wave function or related to wave function, there is an additional quantity to norm, and that is basically the phase. Yeah. So we can always define the wave function in terms of two variables. One of the variable is the probability density, and the other variable has to be the phase of the wave function. Yeah, yeah, or the shape of that wave function. Yeah, because that probability density would have some sort of a shape. Yeah, and so the wave function mathematically can be described in terms of two variables, and those two variables, one of the variable would be probability density, and the other variable would be the phase of the wave function. Yeah, and remember the wave function. So it is a function for a wave. Yeah, and so which is basically the concept which in fact is in fact related to or in fact coming out of the concept of wave particle duality. Yeah. So since the since the wave function psi is a complex quantity, the norm of psi is uh, is given by probability density, but additionally, but in addition to norm, it has a phase. Yeah, this wave function has a phase. And so we write the wave function, we can write the wave function in terms of two variable. One of the variable is rho, the square root of probability density, and the other factor is some exponential function iota S, usko let's say we call it S divided by h bar. So h bar is the quantity which signifies the quantumness of the physical system or the system. And here there are two variables. So we can say that the psi is a function of probability density and phase variable, yeah, and has an additional factor. In this case, this psi has an additional factor which is basically this factor, yeah, and has an additional factor, i.e., the phase which is which is iota s over h bar. So एक्सपोनेंट का जो ई का जो इनफैक्ट एक्सपोनेंट है दैट इज आयोटा एस ओवर एच बार इज द फेस फैक्टर, या सो दूसरे लफ्जों में वी कैन से सो one can one can find uh, Schrödinger equation in terms of, or one can solve Schrödinger equation in terms of two variables, rho and s, in terms of the variables rho and s. Yeah. So therefore, Schrödinger equation क्या है? Therefore, Schrödinger equation is iota h bar psi star, which is equals to minus h bar square upon 2m uh, del square psi plus v into psi, and in terms of rho and s, uh, the the imaginary part, the imaginary part of the probability current J